Here's another fun-filled calculus problem, kind of an exciting problem to do this evening. So we have, it says use identity 2, this is number 14 from 6.4. Identity 2 sine x cosine x equals sine 2x. You all remember and know and love this one from your days in trigonometry. So we're going to use this to find the power series for the expression sine squared x at x equals 0, so the Maclaurin basically. And they give us a hint. We're going to take the Maclaurin series for sine 2x, and then we can integrate it to get sine squared x. And let me show you why that's the case. So let's just go with, we understand, we know this is it's an identity, so we don't have to prove that. And we know the fact that we have integral of 2 sine x cosine x dx. If we were to integrate this, like if I were to say, okay, u equals sine x, my du is going to be cosine x dx, and it turns this into integral of 2u dx, which integrates to become u squared, technically plus c. They kind of dropped that in this case, but so what we're really seeing is sine squared x plus c. Say that quietly there. Now, so this gives us our, we understand now if we were to integrate something like this, we would get our sine squared x. And so technically integrating this, so integral of sine 2x dx would be sine squared, equivalent to sine squared x plus c. So we get that, we can go with that. So we can now look at the Maclaurin series for a sine function, and then if we integrate that, we'll have the Maclaurin series for a sine squared. So I should say, if we integrate the one for the sine 2x. So we have f of x equals sine x, and the Maclaurin for that is n goes from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Now, the slight change we're going to make is that we have sine of 2x. So that means we're going to put a 2 with this x. It's going to be the sum as n goes from 0 to infinity of negative 1 to the n power times 2x to the 2n plus 1 there over 2n plus 1 factorial. And let's manipulate this a little bit. So we'll have the sum as n goes from 0 to infinity of negative 1 to the n, 2 to the 2n, oh, let's see, there's a typo there, right-o, there's a right-o. This should be here, I apologize. 2 to the 2n plus 1, x to the 2n plus 1, over 2n plus 1 factorial. Now we're going to integrate this, and the only term we really have to worry about integrating is this x term. So all the other stuff is just a coefficient. So we can rewrite this. So if we have the integral of n going from 0 to, as the sum of n going 0 to infinity of negative 1 to the n, 2 to the 2n plus 1, x to the 2n plus 1, over 2n plus 1 factorial dx. That would be like saying integral of the sum as n goes from, no. I just said I'm going to pull that stuff out. So that means we're going to have the sum as n goes from 0 to infinity of negative 1 to the n, 2 to the 2n plus 1, over 2n plus 1 factorial. Then we have integral of x to the 2n plus 1 dx. And that's going to give us the sum as n goes from 0 to infinity of negative 1 to the n, 2 to the 2n plus 1, x to the 2n plus 2 over 2n plus 2. And I can't forget we were dividing by 2n plus 1 factorial. So this final step is we are going to be able to combine this expression and this expression. Because a 2n plus 1 factorial is 2n plus 1 times 2n times 2n minus 1 and so on. And so we can combine this and make this the sum as n goes from 0 to infinity of negative 1 to the n, 2 to the 2n plus 1, x to the 2n plus 2 over 2n plus 2 factorial. And that's the answer we're looking for. And yes, I feel uncomfortable not having the plus c, but we're moving past that. Okay, hope that helps.